Welcome to ARIES lecture series. This is the fifth lecture of the series. So, I'll be talking here formation and evolution of stars. Basically, I'll be addressing two questions: that how does a star forms and how does a star evolves? How does they evolve? So let's see a image that you have been seen in the sky. Even if today's sky, this is from Nainital, you see that several features here. The stars with a different brightness, with different colors, and top of that, if uh, you see that the star in the cluster forms somewhere here, also here, and and some gaseous cloud kind of the thing here. So why these stars have a different brightness? Why different colors? One may say that the different brightness, quite possible that at the different distance of the same brightness stars, this is partially true, but other reasons also. And why the different colors? So I'll just flash it. This one, this basically this region is from our galaxy, which is located somewhere here. This is our sun. The region that is visible from the Nainital is here. You can also see from your night skies. Nowadays, due to the lockdown, the sky is too clear everywhere, so you can easily trace out these regions in today's night sky also. So I said that if the stars at same brightness stars at different distance may look, the one is a fainter, one is a brighter. But here I am showing you one picture of the cluster, that is group of stars. They are gravitationally bound with each other at the same distance. So if you see the star here, then you will see that the stars have different colors as well as different brightness. So why the stars have different brightness and why they have different colors? That is brightness I'm talking is here luminosity, let's say, that is energy emitted per unit time, and color, that tells about the temperature of the star. So if you plot these brightness as well as the luminosity of the star in a plane, then you will see the nice diagram here that we call the Hertzsprung-Russell diagram. That basically in 1905, the Danish astronomers Hertzsprung and Russell, they independently made this diagram and saw that most of the stars, they are locating in this line that we call the main sequence of these stars. Why the most of the stars are located here, and the few stars are located here, and few stars are located here, and some of them are located here. Yes, of course, they follow the relation, that is the luminosity is equal to 4 pi r square into flux, where the flux can be calculated from the Boltzmann law, that is sigma t to the power 4. So the luminosity, that is in y-axis here, and this is in x-axis here, the temperature. So just if you are known to the astronomy, that is an absolute magnitude. Magnitude is a logarithmic scale of the flux. And this is the spectral type of the stars. That is a spectral type if O has a more than 30,000 degree Kelvin temperature. Then B, A, F, G, K, and M. This is some classification based on the spectral type of stars. So I'll be not discussing with this the absolute magnitude, and here just concentrate on the temperature as well as the luminosity. If I will put the sun in this diagram, then you will see that this is a 1 solar luminosity that corresponds to approximately 4 into 10 to the power 33 ox per second. The stars have the luminosity that we see in the previous figure up to 10,000, more than the 10,000 at 10 to the power 5 times of the solar luminosity. So that means 4 into 10 to the power 38 solar luminosity will be there, ox per second luminosity will be there. So you have in a single region, we have a different type of the stars. What it tells is that definitely, if you see that here the locus, here are few stars, and if you go down, the stars concentration is going to be increased. So that means the stars, they stay most of the time in this region only. So why there are small numbers? Because it appears that they evolve early, so they evolve faster and they evolve so late. So that means star evolves and they also forms. So what are the clues for the formation of the stars? So these are the few clues. That is, for example, massive O-type stars. That for I'm saying the massive O-type star again. Can you do that? Okay, fine. Sorry. Yeah. So, okay, fine. If you see the massive O-type star, then massive O-type star, that means stars which are very massive. Even if I will say that the star here are very massive and star here are very low mass stars, around a point 3 to point 4, point 2 to point 3 solar mass star, or here is a 30 solar mass of more than 30 solar mass star. So if you see that, then we see in the sky there are the stars which are the massive OTB stars, that is more than 10 solar mass, and their existence in hydrogen 2 region, S2 region you call it, and their lives of these stars are very short as compared to the galactic evolution of the galaxy, very short. So it's of the million years. And there are less massive stars, less than 2 solar mass also, and there are intermediate stars also. So they have a longer lifetime. So you'll see that why they have one has a larger lifetime, one has a longer, smaller lifetime. So where do these star forms? If you see the density distribution, that is basically is constant e to the power minus z over h, where z is a distance from the galactic plane and h is a disk scale height. Then you will see most of the star they form in the disk in the spiral arm of the galaxy. So the stars form inside the relatively dense concentration of the interstellar gas, and thus known as a molecular cloud. So this is extremely cold. At this temperature 10 to 20 degree Kelvin, the gases becomes molecular, that is atoms bind together, and the regions are dense, hence opaque to the visible light. So we cannot see these dense regions in our naked eye. So we can observe them in the near infrared and the radio wavelength because of their low temperature. So these are few molecular clouds that are exist in our universe. That is, most of the abundant cloud is a hydrogen S2, and another one is a CO is also available uh, in the universe. So what are the star forming materials that we said earlier also? That is a discovery of molecular cloud near O types, that is massive stars, because the massive stars are most of the massive stars, they are embedded in the molecular clouds and connected with this S2 region. S2 region have a relatively high temperatures and a low density. The density is low to collapse to a star. So the star has a very high density. So I'll see here that the O-type star, they are in some molecular clouds. They are ionizing the molecular clouds. So what are the basic reasons that they can form the stars? You will see here that the presence of, this is another examples of this is Eagle Nebula, that is pillars of the star formation. You see this is the bright light is the object is behind of this one. Also there are many stars. These pillars are illuminated by the some massive stars. Also here in another example you see that the O-type star is here, so it is illuminating the entire cloud regions. So the presence of massive stars is things. Massive stars have a short lifetime. Massive stars indicate recent star formations. So here you found that the many type of the other stars, variety of the stars, that is called star forming regions also. Massive star distributed uniformly throughout the disk of our galaxy. So star formation, does the star formation occurs everywhere in the galaxy? I don't know whether it's true or not. So mostly the massive star cluster that found around the spiral arms of our galaxies that I saw in the very previous figures. There are some clusters also found in the spiral arms. The star formation is associated with the spiral arms of our galaxy. So This is another example just to show that this is a Orion Nebula cluster, and the star forms in molecular clouds, that we know that from the observations. Star forms in the clusters, that is a group of star forms together. Star forms in the dynamical time scales, that is time scale that is freely falling of the matters. And what is important is that is a feedback. So what is the feedback which triggers these clouds and forms the stars? So it is just one example just to show that example of the Orion Nebula cluster, and this is a Pleiades, that eventually that the cluster like ONC, that is Orion Nebula cluster, has age of the 1 million years, will evolve into the cluster like in Pleiades that has approximately 100 million years. So these are the few evidences of that we can see in the sky through the observations, that there are the clouds, and within the cloud there are the stars, and there are the massive stars. Massive stars have a very high radiation pressure which may ignite the formation of the star. Then we'll see again later slides in. So let's see some parameters here. If you see the density of the interstellar matter is approximately few particles per centimeter cube. Here the molecular cloud of few hundred particles per centimeter cube, and sun is 1.4 gram per centimeter cube. If you convert into this is also 10 to the power minus 16, 10 to the power 16 to 17 gram per centimeter cube. So you see that sun is a star, and we are saying that the star is forming from the molecular cloud. So we need to compress the molecular cloud to form the density around 10 to the power minus 16 to 1.4 gram per centimeter cube. So how can we do that? So that was our aim to understand. So if you see the size again here, size of the molecular cloud is approximately 10 parsecs, tenths of the parsec, where 1 parsec is approximately 10 to the power 18 centimeter. So size of the cluster, that is group of the stars in the together, that I shown in the second figure, is approximately 1 parsec. And whereas the size of the sun is 1.4 into 10 to the power 10 centimeter only. This is the diameter of the sun. If you see this is 18, then you have to reduce this diameter up to this. So approximately 10 to the power 10 times you have to reduce it. So how will you do that? So what will be the forces that can reduces? That is only the force that we have which can contract the material is a gravity that can do the compression. But at the same times we will have the opposite. You will have opposing forces. Gas may have a gas pressure, turbulence. It may have the magnetic fields, maybe the first magnetic fields, because they are in some nebulosity regions, and the radiation pressure. They opposes all these forces. So this is basically the formation of a star is interplay between these two things, that is opposing forces and the contracting forces. Yeah. So the star formation process basically we derive in the two ways, that is spontaneous star formations. Here what you say is that the previously that gravity wins over the various cloud support mechanism, and other one is stimulated star formation. So what triggers these stars to contract, because they are stable in the sky. What triggers these stars to contract? So triggered by some outer inducing conditions, for example the cloud collisions. There may be compression by the expanding S2 regions, where S2 region is basically most abundant things in the universe, and wind from the massive stars. Since the massive stars means they are very highly bright, so they have a high wind speeds. They have enormous amount of the wind is coming from the surface of the high massive star due to its radiation. So it may be the one reasons that they may trigger, the star forming region may trigger and can collapse, and or the supernovae is the another example, that another things which can ignite the star formation. This is the initial mass function. Basically what it tells is that the number of the stars lies in that particular mass bin range is directly proportional to m to the power alpha, where alpha is something like this. Just forget it at the moment. So what are the instabilities in the interstellar gases that is that collapse the clouds? So what we need is that non-equilibrium process are necessary for the star formation to occur. the transform of gas to low interstellar density, that we say that 10 to the minus 23 gram per centimeter, to as a high interstellar density of 10 to the power 2 gram per centimeter. So we need to transform this density to this density. So basically three instabilities are there that we call the gravitational instabilities, thermal instabilities, and ambipolar diffusion. So we'll see that one by one. So first come to the gravitational instabilities that we call also the Jean's instabilities based on the name Jean. So what you call it a Beryl theorem. So what is that? Is if a total energy of a system is E, the gravitational potential energy U and the kinetic energy is K, then the total energy is a half of the potential energy. Then where the half energy goes, that basically radiated away. So if you say that K plus U is equal to E, then K plus U is equal to half U, then you can say in another form of the Beryl is 2K plus U is equal to 0. If K is a kinetic energy here, K is equal to 3 by 2 kT for one particle. If there are N, then multiplied by N. So gravitational potential energy is equal to minus 3 by 5. Gm is square over R. Everybody knows this. So then virial theorem becomes 3 N kT is equal to 3 by 5 Gm square over R. Okay. So if the equality holds here in these relations, then system is said to be the virial equilibrium. If one of them side is bigger, then what happens? If the left side is bigger, then kinetic, that is thermal energy, wins over, then the cloud, whatever is there, will expand here. If the right side is bigger, then gravity wins, then it collapses. So to collapse a cloud, what happened? What we need is that we need 3 and kT has to be less than 3 by 5 gm square over r. So if here n is a density, that is the total mass and mass of the each particles, so r is equal to, in terms of the density, is something like this. So the condition for the collapse is that m, that is the mass of the cloud, has to be greater than this value, that is 5 kT upon gm to the power 3 by 2 into 3 by 4 pi rho to the power half. Here m is a can be converted into the mean particle weight, mean molecular weight, that is m is equal to mu into np. Np is the mass of the hydrogen. So this called is the Jean's criteria for the collapsing of the cloud. So Mj, Jean's mass has to be this. If mass of the cloud is more than this, then the collapse occur. Otherwise, no collapse will occur. So there are some few examples I am giving it here. That is again the Jean's mass. So for diffused hydrogen, the cloud assumed to be entirely composed of H1, where the temperature is approximately 50 degree Kelvin, with the density of 10 to the power minus 21 gram per centimeter cube. M is the mean molecular weight in terms of the proton's rest mass, that is mu, if mu is equal to 1 for the hydrogen H1, then Mj is equal to approximately 10 to the power 36 grams, which corresponds to 100,000 times of the solar mass of the sun. This is a unit of the solar mass. So if the molecular cloud is there, the temperature is less than that, 10 degree Kelvin, density is again 10 to the minus 22, with mean molecular weight is equal to 2. So it is approximately 10 solar mass. So we need to have that minimum mass to collapse a cloud. So the collapsing of the cloud is basically on the gravitational free fall, that is free fall time. So early in the on the collapse, the cloud is optically thin, so it has a low density, so energy can escape easily without absorbed. So the energy collapse is immediately radiated away. So this couldn't want heat up. So this collapse is called the isothermal collapse. And since energy is radiating, nothing is going to stop this collapse. So the free fall time is, we can derive, that is, this is approximation, that is 1 upon 0. Otherwise 3 over 4 pi will be also here. It depends, entirely depends on the density now, the free fall times. Okay. So if density is around 10 to the power minus 18 initial density of this one, the free fall time is approximately 10 to the power 5 years. That means initially the cloud needs around 10 to the power 5 times to collapse, 10 to the 5 years to collapse. So single cloud does not collapse to R is equal to 0, is it not possible? So what happens with the collapse? What stops with the collapse? So that is another point, we call it fragmentation. So as you say that the gene's mass is proportional to t to the power 3 by 2 and rho to the power uh, minus half. You see that from here. You see from here, that is t to the power 3 by 2 and rho to the power minus half. So as the cloud collapses, definitely is inversely proportional to square root of the density. The mass density will rise, the cloud density will rise. Since the collapse is isothermal, a rising density means the gene's mass of the cloud is falling. If the density will increase, the gene's mass will decrease here. So as the star contracts, rho increases, mj decreases. So allow small region inside the gas cloud. Okay, this contains the fragmentation into the small mass to collapse the own to collapse them their own through their own gravitational. So rising density also means the declining the free fall time. That is, as t free fall is inversely proportional to square root of rho. So small dense clumps collapse faster than the overall clouds. So what is happening here? So since the density is increasing, so Jean's mass will be decreasing. So forming of the small regions, that is fragmentation happens. That this contains the fragmentation. The cloud will fragment in the small region. So if they get the Jean's mass limit of Jean's mass, they will again collapse, and the small clouds, the fragmented cloud, they will collapse more fast than the overall clouds because it depends on the rho. So instead of giant cloud to go a monolith collapse, the cloud fragments into small collapsing pieces. So what stops the fragment? Well, this fragmentation always happens. So is there anything that stops the fragmentation? Yeah. So that is basically what stops is the transition where till we are seeing that the isothermal collapse. Now the transition from isothermal to the adiabatic collapse. The process will stop when the condition of the isothermality is violated and Jean's mass starts increasing. At some stages, the evolution of the cloud becomes thick, that is, density rises, hence the opacity. At some points during the collapse, the fragmentation process, the opacity rises high enough that the energy created during the collapse is absorbed within the star itself and it begins heat up. Okay, so what is happening? Density is rising now. Now the heat which is liberating initially was now absorbed and which tries to heat up the cloud. Since the energy is not lost from the cloud, therefore is adiabatic collapse. Okay. So higher the temperature means higher the pressure, so which halt the free fall of the collapse. For the ideal monatomic gases, T is proportional to P to the power 5, hence the density to the power 2 by 3. So Jean's mass then will grow with time. Thus the smallest mass correspond to the Jean's mass at the moment when it makes the transition from isothermal to the adiabatic evolution. The lower limit, what could be now the lower limit of the fragmentations? So to maintain the isothermality, the rate of radiation of energy A is equal to, that is gravitational potential energy divided by the free fall time. So that comes to be something like this, that is proportional to m to the power 5 and inversely proportional to r to the power 5 by 2. The body is the body in thermal equilibrium at temperature T cannot radiate at the rate higher than the black body temperature. So the radiation loss of the cloud is B is equal to 4 pi r square sigma T to the power 4 into F. F is a fraction of how many this one. The F is basically 1. And for the isothermal collapse, that this black body has to be more than this A. B is greater, so B must be greater than A. For the transition from isothermal to the adiabatic collapse, that the B must be equal to A. That has to be given this relation M5 is equal to something like this. So the fragmentation could have been reached in its limit when Jean's mass equal to this value M. So the Mj has to be something like this. That is 0.02 M in terms of the solar mass, T to the power 1 by 4 and mu to the power 9 by 4. So for T is equal to less than 1000 degree Kelvin, F is equal to 0.1, M has to be 0.36. This is so to collapse a cloud can lead to a fragmentation with a masses of the order of solar mass, but or above, but not significantly below that. So this tells till this slides how the clouds fragments, how the cloud collapse, how it fragments, and what to stop the fragmentation, what is the minimum limit of the fragmentations. So now we will see that along to the initially I saw that the HR diagram. So each mass star will evolve in different way in along to this. For example, this is very low solar mass, 0.5 solar mass star. This is 1 solar mass star. They will evolve and reach somewhere here. That is called the main sequence I told here. So the region where it is located, this is called Hayashi track. From the Hayashi track in the chart diagram, so they will go down. So how they evolve through the chart diagram, let's see. So this is basically the temperature density diagrams. How the temperature and density varies during their evolution, during their formation. So this is the corresponding diagram in the HR diagram, that from A to, these are the various steps from A to, this is the radius of 10 to the power 5 where the clouds are located. Then go to the B, then C, then D, then E, then F, finally G. This is approximately the main sequence. So we'll see that how the A, B, C, D, E, and F, G H will reach here. So the collapse here, the spherical clouds. So if you see that, let M is a solar mass, becomes a gravitational collapse at some stage of the collapse of the large cloud and contracts to form a virialized lump with a mean temperature T, that we know that from the virial theorem, K is equal to half of the potential energy, to half mv square is equal to 3 by 5 gm upon Ri through the virial theorems. So for initial temperature Ti is equal to 50 K, the initial radius Ri from the virial theorem, and with the RMS velocity of 10 to the power 5 centimeter per second, it comes to be the 10 to the power 2 into 10 to the power 5, which is the location of in HR diagram here. The initial position was somewhere of the cloud is somewhere here at point A. Okay, the initial phase of the cloud collapsing, the gravitational potential energy is radiating away. So the collapse is isothermal, that we see already, then we are not going to repeat it again. Therefore, the trajectory is simply the horizontal path here from A to B, because isothermal, the temperature is almost constant. During the phase during this phase, the temperature changes very little, but R decreases remarkably. So L is proportional to R square to the power R square into T to the power 4. So here you will see that the luminosity will decreasing from A to B sharply down. So pressure gradient here is okay, fine, I'll leave it here. So the gravity dominates as R it decreases, and R decreases at constant M and T. So if the pressure is negligible, initially the pressure you can assume is negligible because it's a free fall and energy is radiated away of the free fall of the collapse from the equation of motion, that is R double dot is equal to gm upon R square, that you know. So the solution of the equation at t is equal to 0 from R is equal to R0 to density at rho is equal to rho is 0. The t free fall time is again 1 upon 0 0. I just change the notation here. That comes to 4.7 10 to the power 3 rho 0 upon 2 into 10 to the power minus 16 to the power half year. So for dense molecular cloud, again here with this parameter, we get the free fall time is approximately 4700 years. Okay. In really the density may not be the constant, so it will be decreasing towards outwards or increasing toward inwards, increasing inward. So T free fall will smaller for denser inner core and will be larger for the uh, outer core. So the As collapsing of the cloud becomes opaque, the heating will first start at the central part, okay? Because now the central part becomes more denser, so it will absorb the radiations. It will escape. Radiation will escape more easily from the surface. The collapse first stop at the central region of the star, central region of this cloud. So the central core has already reached to the hydrostatic equilibrium, surrounded by still free falling clouds. Core is still in hydrostatic equilibrium. What I'm saying is here is that the radiation pressure, that is gravity, is supported by now the radiation pressure. And but in the outer region of this, still free fall is continuing. So how to collapse this object, how to collapse the cloud to the condensed object? Let m is a mass, if we, and v is the absolute velocity of the flow, then m dot rate of change of mass in that is falling rate of the mass is 4 pi r square rho v. If I differentiate with respect to r, then I will get the equation of the continuity, something like this. For the free fall, again gm upon 2r to the power square root of that. So assuming the mass of the core is constant, then 1 upon rho d rho upon dr is minus 3 by 2r, or rho r is proportional to 3 to the minus 3 by 2. What I mean to tell is this, that ignoring the gravitational force at the central object and treat the rest of the cloud as the homologous collapsing, then the isothermal sphere, the outer thing, is following this relation. That is, rho is proportional to r to the power minus 2. That means the initial phase, the outer region follow the r to the power minus 2, and changing over to r to the power minus 3 by 2 as the density increases. So this is the density, how the density varies in the initial and later stages, that is r to the power minus, from r to the power minus 2 to r to the power minus 3 by 2. So the matter falling onto the core is stopped at its surface, okay? The kinetic energy is then transformed into the heat, part of which is used to heat up the core, and rest being radiated away. Ignoring the heating at core, the radiation losses are, that is basically, we call it again accretion luminosity, is something like half mv square, again m dot v square, because it's a luminosity that I'm using the m dot here. So this is again to the 1 by 4 gm into m dot over r. So temperature does not change during the phase here abc, okay, almost constant. So but during the phase cde, because of the evolution process of the photosphere move inwards, it changes, temperature changes. When the temperature is 10 to the power 3 degree Kelvin, begins vaporize and drops, the opacity drops, radius of the photosphere decreases, approaching to the surface of the hydrostatic core. So because the luminosity remains constant during the phase, therefore temperature increases and decreasing the radius. So during this part of the evolution, a strong temperature gradient is established, bringing the convection into operation. A change in temperature by factor 80 will cause the luminosity by 10 to the power 6 from the initial value, which reaches to the part E of the HR diagram here. So transition from C to E takes place very rapidly. It's not so small. You see the free fall time. It took around, for the some simple example, you see the 4700 years. So it takes around only 300 days. So you may not be sometimes observe this. So it's a very rapid one. So because it is essential caused by the bulk motion of the gases. So here now we reached from free fall to the condensed core. So the formation of the hydrostatic core, again hydrostatic core I am saying is here that the gravity is balanced by the inner radiation pressure. So the mass collapses more rapidly, so time scale becomes much larger because smaller density at the outer surface and pressure gradient breaks the free fall. The collapse of the central part resembles a free fall as long as the matter can get rid of the release the gravitational energy via the radiations. Okay. So central region becomes opaque because density increases, and density becomes approximately 10 to the power minus 13. If you remember that we considered the initial density on 10 to the power minus 13, now it is just 10 to the power minus 13. Further increase in density at the central cause the adiabatic increase in temperature. Pressure increases until free fall is stopped. So this led the formation of the central core in the hydrostatic equilibrium. So with increasing the core mass, decreasing the core radius, a velocity of falling material exceeds velocity of the sound at the core of the energy. So what will happen if the velocity of the falling material exceeds with this one? That the formation of the spherical shock fronts. In this shock fronts, falling material comes at rest, releasing kinetic energy, then radiating away the luminosity of the accreting core. Okay, so in that case, again accretion luminosity is something like this, as earlier we said. As matter is raining down, that is, still the matter is raining down, the surface core is contracting. As a result, the accretion, that is accretion luminosity, that is increases for the constant rate of the mass. So during the uh, contraction, gravitational energy is released in deep interior to the core. So the finite temperature gradient will be there to transport the energy outward. Fine. So how the core collapse here again? So because still we haven't formed the stars, still this is the protostellar phase. So you'll see, sorry. So the accreting protostars heats up and temperature reaches to 2000 degree Kelvin, which dissociates the hydrogen molecules. Not energy, not all energy injected into the gas as a kinetic energy, a fraction of being used to break up the molecules into the atoms, which decreases the value of the gamma, that is Cp.Cp. The S2 molecules, for S2 molecules, degree of freedom are approximately 5, which gives the gamma is equal to approximately 1.4, which is much closer to the critical value of 1.667 for the hydrostatic equilibrium. Okay, so for the dynamical instability, we need to have the gamma has to be less than 1.4, 1.667. So you find that is 1.4. The protostar starts collapsing again here. You see that the molecule dissociates and the dynamic for it follows the dynamic the condition for the dynamical instabilities. So still it again collapse. The central compression is adiabatic as long as the accretion time scale is short as to the Kelvin-Helmholtz time scale. This is basically thermal time scale. We can also call that Kelvin-Helmholtz time scales. So more the more the envelope is depleted, more the accretion rate will diminish, increasing accretion time scale. As it exceeds to thermal time scale, the adiabatic evolution ceases. That will completely ceases. So the temperature increases and reached up to here 10 to the power 4 degree Kelvin, and the ionization starts. The contraction of gas stops only when large fraction of gas is ionized. So here the ionization starts at this point. So later on, again the temperature increases with these ionizations, then starting the nuclear burning on the core of the star. So the contraction along to the Hayashi track will continue as long as energy transport is due to convection. So the evolutionary track will change when the temperature gradient favors the radiative transport, and this will happen at the point F of this in the figure. And finally, when it reaches to the main sequence, that when it reaches main sequence towards the main sequence, so the nuclear burning starts and the star is said to be at the hydrostatic equilibrium. So all the energy, that is gravitational energy, the free fall will be supported by the radiation pressure of the star. So the main sequence phase that we call, that is range of stellar masses. The main sequence is the locus where stars burns etch into the helium to the core. Object which cannot reach the necessary temperature and density to ignite the fusion because of their low mass that is less than 0.09 solar mass are basically called brown dwarfs. High stellar mass is step up by Eddington limit, that is the maximum luminosity through the Eddington limit, that is 3.2 10 to the power 4 m over Mson into Elson. That depends on the mass. If that limit, the luminosity may not be more than this. Okay, so this is basically the first part, that is a star. To form a star from a cloud to a very small condensed object, we reduces the density, we reduces the size by using the uh, Jeans instability, and there are other reasons that I am not touching here. That is the, the, the collapse can be stopped by the ambipolar diffusion, that is because of the magnetic field as well as the turbulence. There are several things, so that I am not touching it here. So I'll come to the second part, that is I have reached the star somewhere here. I have reached all the star. This is called, if you join this is called again main sequence. So most of the star were reached. Initially they were located somewhere here and they reached here. All the star reached here. So I need to evolve them again to back direction. They will evolve again, go to the similar path and follows this path and reached here. Let's see that how the star evolves. So a star of the different masses evolve off the main sequence along the different paths of the star diagram. So these are the different paths of they are the evolutionary tracks of the stars. So it depends on their mass. If this is a very 0.5 solar mass and this is a 15 solar mass, evolution of the 15 solar mass. So let one by one we see that how the star evolves. So I'll just briefly tell you the time scales on the main sequence, that how much time the star stay in the main sequence. That is basically the nuclear time scale. What we call the nuclear time scale is basically the time scale in which a star radiates away all the energy that can be released by the nuclear reaction at the core, because the star, what is happening, we reach the temperature 10 to the power 4 degree Kelvin. Then later, due to the again condensations, the temperature reached to the ready for the hydrogen burning in the core. So when the hydrogen burning in the core, then we say the star is a young and reached to the main sequence. So here the hydrogen burning is happening, through the nuclear reactions. So time at which all the available hydrogen turned into the helium. But only 10% of total mass of the hydrogen in the star can be consumed before other more rapid evolutionary mechanisms set in. So not more than this one. So nuclear time scale is basically given by this. So for the sun, it approximately 10 to the power 10 years. For the 30 solar mass stars, it's very less with respect to this, around 2 million years. So if you see that the sun is somewhere here, one solar mass, it takes longer time. Even then this star will take much longer time to stay here, and if you go up here, they will take shorter time to stay here. For example, 30 solar mass will come somewhere here, so it will take only a million years to stay in the main sequence. So life on main sequence. So burning of hydrogen into the helium changes the chemical composition and lowers the pressure. So again, what happens if because hydrogen converting to the helium, so the core shrinks and heats up and burn H at higher rate. So luminosity increases, that means radiation pressure increases, which causes the outer envelope to expand. So the main sequence star begins on the lower edge of the MS band and moves up towards the right, like this, along to the red line for these two stars. Okay. So what is happening basically? Hydrogen converting to the helium. So the core shrinks, again it will heat up. So if it will heat up, then temperature will increase. So at the result, the hydrogen will burn with more higher rate. So luminosity will increase because the radiation pressure will increase, the luminosity will increase. This try to expand it. If it will expand, it will increase its slight radius, but a small decrease in the temperature. With this combination, it will goes from 1 to slightly increase in the luminosity and as well as decrease in the temperature here. So this is a phase 1 to 2 in the evolutionary track of the star. Second thing, so on the main sequence, star is in hydrostatic equilibrium. As we discussed is now, the star has already reached to the hydrostatic equilibrium, and its core is sufficiently hot to fuse the helium, is sufficiently hot to fuse hydrogen into the helium, because you have already the million degree Kelvin there. So star has a two chemical zones, a core of inert helium, because hydrogen is converted to helium, surrounded by H. A core of star is not sufficiently hot because the temperature is still 10 to the power 6 degree Kelvin, that is a million degree Kelvin. So to fuse the helium, you need around 10 to the power 10 degree Kelvin, approximately that. So, so without energy generation, core cannot support itself against the gravitational collapse because no energy generation happening in the center at the core. So who will support the gravity here now? So without any energy generation, no support of the gravitation, hence the star will collapse against the gravitational collapse, and it begins to shrink and heats up again. So that is, if it begins to shrink, that is phase 2 to 3 here. Okay, this is 2 to 3. So slightly, because it's collapsing, slightly increase the temperature, hence the increase the luminosity. So ends of the main sequence, that is cell burning of the hydrogen. So this heats the transferred in the cell of H core where the temperature increases, so H fusion is can occur. What I'm saying is that now the free fall is again going there because in the center there is a helium, the temperature not too much, so the temperature in the outer surface will increase, which try to increase the hydrogen fusion in the cells, not in the cores. So the cell burning occurs rapidly, causing the envelope to slightly expand, because if it is burning, nuclear reactions are going there, the radiation pressure increasing, so increasing the envelope here. So you will see that the phase 3 to 4 here again. So if it is increasing, the temperature is slightly decreasing, radiation is increasing, and slightly increasing the luminosity here, that is 3 to 4 phase. Okay. So now coming to the 4 to 5 phase. So how the star evolves from 4 to 5 phase. As the core continues to collapse, the temperature of the H fusing cell continues to rise, and thus the luminosity in the cell increases, as does the pressure. The entire star is no longer in hydrostatic equilibrium. Okay? And the envelope begins to expand. See, the fusion is going on the cells, which is increasing the luminosity and the radiation pressure, and it's not in hydrostatic equilibrium and try to expand. The envelope begins to expand. As they expand, that envelope expand in the outer layers, becomes cool, the star becomes redder. While its luminosity increases, the star is slowly ascends to the RGB branch, that is red giant branch, that we call it here. So this is a very rapid process and difficult to observe the star during this stage. The star in this region in the HR diagram is called Hertzsprung cell diagram. That is, HR diagram will found in the HR diagram a gap here, no star will found here. So in the HR diagram, so that is called the HR gap, Hertzsprung cell gap. So that phase is 4 to 5. So this imbalance will continue until the star finds a source of core energy generation, that is a helium fusion. So what is happening here? Now that it's becoming a cool, temperature is becoming cool, it's expanding. So if so, the H fusion leaves behind the helium as in the core of the star, which cannot begins to fuse until the temperature of the core reaches to 100 million degree Kelvin. Right? When it reaches to the around 10 to the power 8 degree million Kelvin, at 10 to the power 8 degree Kelvin, so how the star begins helium fusion depends on its mass. Okay, if mass is more than 3 solar mass, then it contracts rapidly and core heats up and helium fusion begins gradually. Less massive stars evolve more slowly and their cores contract so much that degeneracy occurs in the core. So when the temperature is hot enough, helium fusion begins to make energy and the temperature rises, but pressure does not increase due to degeneration. Higher temperature, helium fusion even further resulting in a runaway explosion. The helium flash, which for a few minutes can generate more luminosity than the entire galaxy. So that is basically seen it here. So somewhere at the phase 5 to 6, that is called the helium flash. So T increases, helium fusion even further resulting a runaway explosion. The helium flash, which for a few minutes can generate more luminosity, which is the entire of that galaxy. Okay, the flash does not destroy the star. The envelope absorbs the entire light because the outer envelope is the expanded one. So it absorbs all the energy, which is shown in here in the phase 5 to 6. So we reached from phase 1 to 2, 2 to 3, 3 to 4, then 5 is basically red giant branch, and 5 to 6 is called helium flash. It's sudden flash comes here. Okay. So what will be the end of the red giant phase? This is a 4 to 5 is a red giant phase, 5 to 6 is a helium flash. So now the core has heated up to 10 to the power 8 degree Kelvin, that is 100 million degree Kelvin, and this new energy source stops the rapid contraction. Okay, now at the core the helium ignition started, that is helium fusion started here. So with burning of the helium, the star again reaches to the hydrostatic equilibrium. The helium burning starts cores to expand and envelope to contracting again. The star is in quasi-static equilibrium again, we'll say. The lifetime of the star in this phase, at the red giant phase, is approximately 10% of the main sequence lifetime. So as a low mass star goes, as low mass star ages, convection occurs over a large portion of its volume. See, that I'm not touching it here, but the transport of the energy from the core to the surface in the low mass star is a different, and in the high mass star is a different. In the low mass star, somewhere here up to here, the core is a radiative, through the radiation, all the outer envelope is a convection. Here the star is fully convective, the entire thing is through the convection, whereas the star is the massive, the inner one is the inner part of the star near the core is a convective, and outer one is a radiative. This is I'm not touching it here, but just forget it. So as a low mass dagger, this takes heavy elements formed in the star because the convection is taking place. So this takes whatever the heavy element they formed in the outer part, the stars in the interior, and distribution them throughout the star. This process is called dressed up. That is phase 6 to 7. That is called dressed up when there is a distribution of elements inside the stars through the convection. So yeah. So now what happens? We just reached to the 6 to 7. Now see, now this is again coming to the left. We are going from right to left, then left to right. So this left right goes on. So now the evolution is similar to the main sequence evolution. Expect the helium has replaced by the H. What is happening now? In the core initially there was a hydrogen. Now the hydrogen is replaced by the helium. It's quite similar to the main sequence evolution again. So how the star will reach the main sequence, that is coming from the left to right. The helium burning increases temperature and the luminosity of the star, that becomes that increases temperature as well as the luminosity, that becomes 7 to 8 both slightly temperature, hence the luminosity. Okay, because that the helium burning will produce more temperature, more heat, that is a phase 7 to 8. The evolution between 7 to 10, that is from 7 to 10, is again very similar to 4 to 5, except that we have a core helium burning, then the hydrogen helium burning. So part 7 to 10 in HR diagram, I will just put it. Part 7 to 10 is HR diagram. That is called the horizontal branch of the stars in the HR diagram, populated by the stars of the helium burning core and hydrogen burning cell. The cell is in the cell. Please keep in mind, in the cell, the hydrogen burning, that is nuclear burning of the hydrogen, is still going on because the temperature is too high there. The evolution of the cell helium burning is replaced by the core helium burning, similar to the phase 7 to 10. Upward evolution along to the Hysic track is known as AGB, that is asymptotic giant branch. This one. So that is, we see initially that the Hysic track was also somewhere located here. So after evolution, what we did is that we evolved the star, we formed the star from this Hysic track and reached here. Again, we are going back to here with this left rights and reaching to here. So upward evolution, that is called upward along the AGB, is along the Hysic track, is called asymptotic giant branch. So the end phases of the stellar evolution are basically that will be taken care by another lecture in a series. So I'll just let you know that the evolution and eventual fate of the star in the late stages of their lives are critically dependent on the amount of matter they have at birth. So if mass is less than 8 solar mass, they will end as white dwarf and RGB envelope becomes planetary nebulae. If more than this, their lives end their lives at the supernovae explosion, and stellar remnants are maybe the neutron star or black hole. So that will be taken care in probably in next series of the lectures. So I'll stop it here and thank you very much for joining with us. Is the question?
Okay, here is a question. One second.
No, Pradeep, Proxima Centauri is the star to the solar ones.
Okay, sir, I think you can first read the question and then answer.
Yeah, Pradeep, yeah, Silpa has asked that what is the source of turbulence? And the second question is Proxima Centauri a massive star? No, it's not massive star. It's a star similar to the sun. And please let me know the formation and lifespan of details for the same. The formation is a formation of the Loma star at the sun forms. If I remember correctly, it's a M-type star, and its a lifetime is a very large lifetime. It's around 10⁹ years, more than sun, because it's later spectral type. So it is, what is the spatial scale up to which the cloud collapse? Yeah, that is called the Jeans length, that we can convert the Jeans mass into Jeans length. It's quite easy to convert it. Yes, you said that the velocity track of the more massive stars, that is more than 15 solar mass, seem to a so smaller negligible the helium flash. Yes, yes, because their lifetime, the evolution is lifetime is too short.
So that is not visible. Yeah. So one more question is from Gaurav Singh. Yeah, these two questions you can answer.
Does these time scales during the helium flash process depends on the mass of the star itself, or it is around a few minutes of all? No, it depends. Definitely depends on the mass.
Yeah.
It's varying mass. Yes. And,
can we relate?
what
last one.
Can we relate space expansion, and this is by the Vishnu Patel, can we relate space expansion and star grow bigger and in its life cycle? Yeah, star will grow to bigger. That I understand, because as soon as the radiation pressure becomes large, the star becomes red giant that we saw in the evolution. Yes, it becomes larger.
So these were the questions. No more questions.
Okay,
Yes.
thank you very much. If someone misses today's live lecture, they can find in ARIES Facebook page and also on the ARIES YouTube channel. Please, you may ask, and I'll be happy to answer these questions. The links to these sites are available on ARIES official website. So you can submit your questions later on and also provide your feedback by using the link available below the videos. Thank you. Thank you for joining.